And he's a biophysicist, and he's going to tell us, I think, about AlphaFold and biophysics and thermodynamics. Take it away.
Great. Can people hear me in the back? So today, I finally understand what people mean when they say that in quantum mechanics you have delocalization. So I gave a talk in the main venue in the morning. Now I'm here, and unfortunately, I have to be at a panel at 12:30 in the other venue. The energy is exciting, though. So my name is Pratyush Tiwary. I'm a professor at University of Maryland, not too far from where John works. And I have an appointment in three different places, but physically I'm located in an institute called IPST, or Institute for Physical Science and Technology. For those of you who don't know it, this institute has been at the forefront of statistical mechanics for the decades. When we talk about free energy perturbation, or FEP, that's all due to people like Zwanzig, and I do my group meetings in Zwanzig's old office. So it's a very exciting place to be thinking about StatMech. Let's see how this works. So, and I have a very diverse group made up of students from different backgrounds: biophysics, chemical physics, physics, even have a postdoc. That's kind of cool. And in the past, I have had mathematicians. Luke is now a postdoc at Flatiron. And today's work that I'm going to show you is mostly due to my PhD student, Akash, who is finishing up this year, and Lucas, who is also finishing up this year. And we still have a position for one postdoc, so please apply if you're interested. So, and these are the sources of financial support and computer support, and these are my conflicts of interest. So let's get started. So my lab is interested in three different problems. One is, well, there you go, Glivec from Hannah's talk against Abel kinase. So how do small molecules dissociate? What is the role played by protein flexibility? And can we use molecular dynamic simulations to predict what is the residence time of drugs in proteins? This is a problem I started working on. And just to give you a context, I don't have any degree in biology or chemistry, for that matter. I was trained as an engineer, material science, and then I went to do a postdoc at ETH, and I worked with Michele Parinello. And within the same 1 month, I was working on alanine dipeptide and drug unbinding, so it was kind of crazy. But we published some of the first methods using metadynamics to calculate residence times around 10 years ago. Now some of these are commercialized by Schrodinger. You can use a tool, and you put in the PDB, and you put in the, well, basically you put in the crystal structure, and 2 days later it gives you the pharmacokinetics, it gives you the residence time of the drug. And there's a preprint out on it that you can read, and my group is continuing to improve these methods. We are very interested in RNA structure prediction. I will be talking a bit about that today. This is, in fact, the first time I'm sharing the RNA work in a public setting, so that's very exciting. And a big part of my group, supported by the Department of Energy, is interested in how phase transitions happen in general matters. I won't be talking about that today. So I started doing enhanced molecular dynamics, or molecular dynamics in some form or the other, as a second-year undergrad, back in India in 2005. And I thought, surely no one will be doing molecular dynamics like 15, 20 years from now, and especially there will be no need to enhance it. Computers will become very fast. 2009 is when Kristen Lindorff Larsen and D. Shaw published a paper on how fast folding proteins fold. It was the cover of Science. And you thought, okay, we have reached millisecond now. It's done. You're soon going to be doing minutes of molecular dynamics. It didn't happen, and the problem continues to be super high profile. It's kind of crazy how much high profile it's getting by the day. And there are lots of claims. I mean, and it's all connected. I mean, a lot of the field, like someone said, the field, we would not be in this room if the PDB was not there. I would also argue we would not be in this room with the same energy level if this had not happened. This was something. It was like, it's fascinating, and amazing, and also, of course, very well deserved. But now there are a lot of things coming with very high-profile news and stuff, so that we can reproduce the whole process of molecular dynamics with generative AI models, and lots and lots of methods. I need to update this slide every week, because there is just a new method all the time. Have we done everything though? And I like to think about this also for the younger students in the audience. You want to think about problems. So yesterday we were in a panel in AI for physical sciences, and Yasha Sol-Dickenstein, who invented diffusion models in 2015, basically said he believes in 6 years there will be no need for his intellectual capabilities. This is the boldest statement about AI and what it's going to do for science I have heard from someone who I deeply respect. It's like I'm still processing it. So it's important to think about problems where there is data scarcity, where there is some scope for novelty, right? Where we, like Hannah also showed in her work, you have to curate data in a very particular way, and you have to think about what to do. So with AlphaFold, of course, we have made huge breakthrough in predicting the most stable structure of well-structured proteins. But that's a grand challenge, which we have solved this part, but we are still struggling in how to get the new conformations, right? To some extent, even the problem is somewhat ill-defined, like how do we compare what's going on over here? But then we also have disordered proteins and RNA, which is a big part of the genome. And it's interesting to see what happens in CASP in the coming years in predicting structures for things like this. And then the third problem, which I'm most interested in, is that even this, for a structured protein, you might think the landscape is kind of stable if you change the temperature or pH. But if you get to IDPs or RNAs, the landscape can be completely temperature and pH dependent. An example which I like a lot is RNA thermometer. This one is involved in this particular virus. When the mosquito carries it, it is in a certain conformation, which is non-lethal. It cannot replicate. As soon as it enters a human body or even a bird, the temperature changes and the conformational landscape changes. And the RNA takes another conformation, which can actually replicate rapidly. And then it's boom, it's game over. So how do we predict? We don't want to just predict the most stable structure. We want to predict the ensemble. Furthermore, we want to predict how will the ensemble change as a function of other factors. So what would be a naive way, or one way of doing it, would be to collect multiple copies of the PDB, right? And it looks sort of like the matrix, right? You have PDB multiplied by PDB multiplied by PDB, where you have a collection of information at different temperatures, conditions. Maybe you even supplement it with molecular dynamics if you trust your force fields, if you trust the sampling in molecular dynamics. It's one way of doing it, and I think we should keep collecting more and more information, but I think it will fundamentally be sparse. It will not be enough. We will run into risks of overfitting, of memorizing, and not truly learning. So what my group has been doing since I started my lab in Maryland 8 years ago is to think about how to combine methods with statistical physics and artificial intelligence to come up with approaches which sort of get the best out of data and try to really extrapolate across out of distribution. So I will be talking about both these methods in how much time I have. I will mostly talk about AF2-RAVE, and I'll show you a little bit about RNAnneal. This is where we have commercial interest, so we filed a patent. It will be publicly out in 2 weeks from now. And so let's get started. So we will talk about AF2-RAVE or AlphaFold2-RAVE. So our first motivation here is, how do we compress information? What does it mean to think about a protein in a reduced dimension space? We can take an autoencoder and compress all proteins and look at the latent space of the autoencoder. But then what we are doing there is the input is the protein, and the output is also the protein. Do we really care about that? We know biological systems exist in different metastable states. So perhaps instead of trying to take the protein and predicting everything that exists out there in the system, that's overkill. We don't want to do that. So our motivation is, like I said, biomolecules exist in metastable states, and that's the first motivation. And second motivation is the number of metastable states is a function of your time resolution. If you're looking at a system where you're collecting information, which is averaged over a microsecond, the number of states you get in the system will be different from the number of states if you were looking at the system with averaging over every nanosecond. You will have more states if you looked every nanosecond, right? So this is our motivation. How do we work with this? We use what is known as an information bottleneck. Information bottleneck has a long history. Actually, the first person to think about information bottleneck was Shannon, in 1950s, when he worked on something called rate distortion theory. So around the world wars and stuff, he was interested in thinking, how much can you compress a signal so the main aspects of the signal can be recovered by the other side? We don't use rate distortion theory, really. What we use is a form introduced by Bill Bialek, and that's the form here. So what we say is, if we have a biomolecular system, and let's say we have features, these could be all atom coordinates, or these could be features where you have already taken care of the symmetry. For example, instead of positions, you look at distances. So what we are going to do is to fit a model which tells us the future state of the system. So it takes as input all atom coordinates or distances at time t, and then it tells us what is the future state of the system. So, and this can be mathematically written down as a difference of two mutual informations. You want to forget as much as possible while still being as predictive as possible. So you don't want to over-memorize, but you still want to be predictive. So And we have a lot of papers related to this information bottleneck framework. You can read, particularly this is the main paper where we show how this is connected to what in chemistry is known as the committer, which is so-called perfect reaction coordinate. So there is a good theoretical basis for using this. I won't be getting into much details of how this works. One thing I want to emphasize here, the prior makes a huge role. So in an autoencoder, a variational autoencoder, you use a single Gaussian prior. Here we use a mixture of Gaussians. And the number of Gaussians is updated on the fly, so it corresponds to the number of metastable states in the system. And I can come back to this later if there is a question. So with this, what we can do is to so that's taking data, taking some molecular dynamic simulation, and learning a reaction coordinate or an information bottleneck. But what do we do with that? With that, we can do enhanced sampling. Methods like metadynamics, umbrella sampling, weighted ensemble, whichever method you want to pick. We prefer metadynamics and umbrella sampling. These two dependent on many reasons. Weighted ensemble is very accurate. The boost we get in time is not that much. And so in this case, this is, for example, an RNA. You take some trajectory. You learn an information bottleneck. In the early rounds, notice I keep a linear encoder because the data is so noisy. If you use a nonlinear encoder, the bottleneck will probably be just capturing noise. So you keep iterating, and this whole framework is called RAVE. It's clearly one of those methods where the acronym came before the full form, okay? So I was a first-year professor, and I was just like listening to a lot of rave music all the time. I don't know why. And I was like, okay, I'm going to call this rave. So, and then we tried very hard to come up with a full form. So that's fine. So this is the RAVE framework. We have used it for a variety of things, and I want to show you how we implement it in context of AlphaFold 2. And RAVE would not have been useful if we did not have AlphaFold 2. AlphaFold 2 is critical for this to work. And of course, we can replace AlphaFold 2 with other things like Laurent Porter's methods or any other methods that you have to generate alternate conformations. We mostly work with the MSA subsampling approach of AlphaFold. And if you're interested in the code, I recommend going to this. It's open source. You can play with it. And this paper in Digital Discovery explains all of this. So we take a sequence. We sample a bunch of different MSA depths. Some of them can generate unrealistic structures. We remove them. Then we perform some sort of clustering. First we have to predict what are the most variable important features. There is a whole method that goes into that. We do some clustering to launch our molecular dynamic simulations. From those molecular dynamic simulations, we learn this information bottleneck, and then we are able to look at different conformations that exist. I will show you in action how it actually works. So kinase, a different one from what Hannah showed. This is DDR1 kinase. DDR1 is a nice system because John Codera and Sonia Hansen and others did a lot of Markov state modeling on this. So we can compare apples to apples. You know, we can compare our stuff to other simulations. So at least we are robust. So in this case, we can take reduced MSA subsampling AlphaFold. It's actually not very easy to get the activation loop to flip. This is a big movement. This is a movement of 15 angstroms or something like that. It's easier to just get the DFG motif to flip, but if you try enough, if you generate on the order of 1,000 structures from AlphaFold, you can get one or two of them where the activation loop would have also flipped. So, and then we run our protocol, and you can see we get the right distribution in the free energy, and we get population of different states. So all of this is fairly automated now. You start from the sequence, and it gives you all of this. There is yet another benchmark. This is the COVID spike protein receptor. So in the top figure, I'm showing you the structures that you get out of MSA subsampling. The underlying thing is the free energy from a very long 2 millisecond unbiased MD. So you can see that MSA subsampling gives you a lot of structures. It covers a lot of the space. Many of them are junk. They are very, very high energy. And a naive approach, so instead of using this information bottleneck or whatever, a brute force approach would be to take the 1,000 structures that you get from AlphaFold 2 and just do MD from each of these 1,000 structures. But that's not very smart, right? You're wasting a lot of compute time on doing these things. So a big part of the business here goes into learning where to launch the MD from. And that's what we are able to do with information bottleneck. These are our cluster centers. We launch our MD from there. And then this orange thing is the coverage from our MD. Our MD is, so the reference is 2 millisecond MD. The orange part that I am showing you is around 200 nanosecond MD. So it's 6 orders of magnitude or something like that. Several orders of magnitude faster, and you get very similar coverage as you would get from unbiased MD. This is a very brand new work. My student just finished this slide yesterday. I'm very happy to show this. So BioMU is fantastic, and they have this Frank curated a data set there called OOD60. So OOD60 is out of distribution 60, which means that the proteins in OOD60 have at most 60% overlaps in sequence similarity with stuff in the PDB on which AlphaFold 2 was trained. So this is a great system for us, set of systems for us to compare our methods with. In this paper, which will be out next month some point, you will see more systems. I'm going to show you 4 over here, and I'm going to be very honest in showing you when does AlphaFold 2 Rave not do a good job, and why is that the case. So for example, this is one particular protein. So look at BioMU's prediction. Number one, it does not do a very good job. No method does a very good job of getting you close to the actual reported crystal structure because the ligands were pulled out. We are doing things on APO, so it does not really work that well, but still. So you see what BioMU does, it gives you coverage, but it's sort of a blur. It starts from here, and there is no other way of describing it except a blur. It just goes out, and it gives you some coverage. If you wanted to do docking, for example, on this, you cannot sample Boltzmann. The Boltzmann weights are not correct. It's just sampling something. While we actually get little pockets, and we get where are the metastable states. In this one, you can see the coverage is really interesting. So the most stable, in fact, the most stable state getting from BioMU is not the same for the apoprotein. It's somewhere out here. For this one, we don't do a good job. We never escape to the other basins. It does not happen. I don't know why. And in this one, again, you see the most stable state is the same, but it goes out and explores these other states. So it's a robust way. And we don't have these training leakage type of issues because all we are doing is to run molecular dynamics in a very clever way. Or I wouldn't call it clever, but in an efficient way. So, and then we are doing a lot of fun stuff with AlphaFold 2 Rave. This is a collaboration with David Weber and the University of Maryland. He is fascinated by this protein called S100, which is a calcium binding protein that's implicated in many diseases, including Alzheimer's. And it's also very interesting. My postdoc, he's actually a bad boy sometimes, right? He gets anxious. So I was looking up doggy Xanax, like to make, so he's on gabapentin, but there is, he has a therapist, what can I say? So this protein is actually even used to come up with like dog relaxing things, so this is very interesting. It's so far there is no one drug that made it to phase 3 but did not make it further. So in this one, we have this whole protocol where we run AlphaFold 2 Rave and we sample global basins and pocket basins. This plot will take me a few minutes if I really went through it carefully, but the big picture over here is, if you look, so what we are doing here is docking enrichment studies. David had some ligands which bind with some affinity, which are not in the PDB, and we can put a lot of decoy ligands, right? And by the way, Brian Schuckert was very helpful to us in that we do this very carefully. So what we can do is to take the 10 ligands that David had and add 1 million other decoy ligands or 2 million other decoy ligands and see at what number of ligands do we have to screen before we get the correct structure. And what we find, that the message of this plot is what we find is, number one, AlphaFold 2 Rave does better than just taking the AlphaFold structure. That's fine, but it even does better than the crystal structure that David himself had for this one, because it captures the side chain movements and things like that. It induces that type of flexibility that if you are using simple docking software, if you use Glide, then it won't matter because induced fit docking will take care of these things. But you're using something like dock, it does make a difference to dock against AlphaFold 2 Rave structures. How much time do I have? Okay, I will show you very quickly. 10 questions, right? I do have to go to the panel also. So I will tell you about what we are doing in RNAnneal. And I'd like to say that my dog is an expert on diffusion models because I actually managed to, this PNA as the figure 1 is his photo, I'm very proud of that. Converting him to noise. So we started working on, no, I don't want to. We started working on diffusion models around 2020. In fact, I remember it was Biophysical Society and possibly the last time that John Jumper and I gave a talk in the same session. And we talked, or maybe not. And back then, I don't think John was very much thinking about diffusion model. He had still started, but not a lot of people were working with diffusion model in 2020. If you look at the citations, it started picking up right around then. So, but to us, it made just a lot of sense for a lot of problems. So it's really nice to see how everyone is picking up, and I think I also anticipate the newer models will keep up. Stochastic interpolants are starting to be even more powerful. But I will show you what we are doing here. So if you like to read comics like I do, and especially Asterix, which I like a lot, so depending on whether you are from France or not, is there anyone from France here? Do you know the name of this guy? Panoramics. Anyone else has a name for him? In English comics, he's Get-A-Fix. So he's the village magician, right? So there is this little village, and the Romans have conquered everything else except this village because he has a magic potion. And it's a long story. We don't have to go into asterisks, but I want to show you the motivation here. Our motivation is, let's say you have a biological system or a material system, and you are doing simulations at 4 different temperatures. Why do you want to do simulations 4 different temperatures? Because often at the temperature of interest, you are just trapped, right? You don't escape from one metastable state to another. If you heat it up, you can very quickly go to elsewhere, right? So this is something that has existed for a long time. People do such simulations. The first person to introduce such an idea was Giorgio Parisi, who later won the Nobel Prize, not for this, but for something else. Then in Schrodinger's FEP+, this is what is used, replica exchange with solute tempering. The reason they have to use solute tempering is because if you exchange information across these systems, so the idea is the very hot system is going everywhere, the cold system is trapped, so you periodically exchange information. So the problem, of course, is that if the system size is large, the probability of exchange goes to 0. And this is central limit theorem. 1 over square root of n, it starts to go to 0. So what people do in solute tempering is they have tricks to deal with this, but it has its own limitations. So what we do is to take this approach, and this is why Get-A-Fix or panoramics comes in, is let's imagine we take all these different simulations, and in post-processing, we throw them into this magic pot. And this pot is such that now we can extract samples at any temperature of interest, including the temperatures at which we want, but also temperatures where we did not do the simulation, or temperatures cooler or hotter than the simulation of interest. And for this, we use diffusion models. And we first published in this paper, but if you really are interested in this, I recommend reading this second PNAS paper, which is called Thermodynamic Maps. And one of the reasons why it works very nicely is that we don't do diffusion just in feature space, but we do diffusion in the space of features and their fluctuations. Fluctuations are what capture information about the environment. And that was the key insight in this method to work, and it works quite nicely. Now, I'll show you what we do. So for example, this is a system that in statistical physics, at least 2 Nobel Prizes have been given for it, and I predict there will be at least 1 more. And the idea is that you have a bunch of magnets which can align in the same direction. At very high temperature, everything is disordered. At very low temperatures, the magnet aligns in the same direction, and you get a magnetization versus temperature curve. So here I am showing you that we take thermodynamic maps and collect data at only 2 temperatures, and we train it to get the whole magnetization versus temperature curve. Not just that, we get the heat capacity spike. There is a phase transition going on. We even get the critical exponents right. So to get this level of accuracy in Ising model was really, really satisfying. So how do we go from Ising model to RNA, and is there any connection? Yes, like I mentioned. Yeah, and we can do it on other systems also. So Parisi, who I mentioned, in 2000, he was already thinking about, and this is the only RNA paper by Giorgio Parisi, I think, which is interesting. He was already thinking about how to use Ising model and specifically spin glasses. Now, spin glasses are also used by a lot of people to understand how machine learning works, to model RNA structure, secondary structure. So it's a cool paper. So with that, we were able to do all of this, and now we can look at RNAs. These are model systems. So this is GCA tetraloop. This is HIV-TAR. Look how rugged the landscape is. This is anything but a funnel. And the number of states in the system completely change as a function of temperature. This is work done by my fantastic postdoc, Yunrui Q, together with PhD student Anjali. You can see how all of it changes. And with this, I can finally tell you a little bit about RNAnneal. And I'm deliberately using this impressionistic style picture of a haystack. So our approach here is to think about RNA structure prediction as finding a needle in a haystack problem. So it's similar to AlphaFold Rave. If some AI method can generate candidate structures, can we go and rank them? And can we find the right structure from them? If your haystack is missing the needle, there is no hope. It's not going to happen. But if the needle is there, how do we find it? So yeah, I'm not getting into the details because of this, but the idea is to start with some physics-based sampling, which means a bunch of different methods, train thermodynamic maps, and get a weighted ensemble of tertiary structures. And it's fully unsupervised, and it does not just give you the one structure, it gives you an ensemble of structures together with their populations. And I like this plot a lot because it shows how RMSDs can be deeply misleading for RNA. If you're small RMSD, it may be okay, but on the y-axis, I'm showing you what is known as an interaction network fidelity, or INF. So INF should be close to 1. It's like a contact map. So when you go to small RMSD, from the reference structure, the INF is close to 1. As soon as you go above 5 or 6 RMSD, you could have 2 structures with this 10 angstrom RMSD accuracy, but their INF would be completely off. They could be completely different structures. Does this mean we should look only at INF? No, RMSD still captures some information. RNAs are just messy. You have to take a 2-dimensional picture. And for example, for this NAT plus riboswitch, I can show you here that this is the crystal structure. And from RNAnneal, we get 5 structures with their thermodynamic weights. And notice that the crystal structure is actually 5th ranked, the most dominant structure that we get. And there could be many reasons here. Number 1, the ligand has been removed. Number 2, we are doing with force fields of different sorts. So, but we do get, so we are very excited about the next CASP to take part with this method. And yeah, and we can use this to do many things. Like I said, it can also be used on top of other existing structure models. Boltzmann, AlphaFold 3, Chi1, Chi2, Chi3, whatever, You generate a bunch of structures from them, and you use our procedure to actually go and rank them, and a bunch of other stuff. So I will conclude here. I showed you today 2 methods. I mostly spoke about AlphaFold to Rave or AF to Rave. The code is out there. RNAnneal, the preprint will be out in a month or so. We have a patent. And Emergent is a company that I started a year ago. Until a few months ago, it was the company really meant me getting offers to start bank accounts, like spam after spam after spam. But finally, we just raised $130,000 from TEDCO, which is the Maryland equivalent of SBIR, which is quite nice for us. We have some optimism now, and we are doing a pre-seed raise for this company. It's based around RNA, but really moving on to IDPs and really doing therapeutics around systems where the single structure paradigm is not sufficient, and you really need, and you cannot just train ML models on the data because it's not there. And I will be happy for more questions. Thank you.
Thank you for the talk. Hi, thank you for the talk. You described 2 somewhat different choices of enhanced sampling method for what initially you might think would be fairly similar problems. And so I'm wondering if you can talk a little bit about how the choices that you made for proteins versus for RNA are kind of the right choices for those tasks.
That's a very good question. And I had a slide on it, but I really wanted hard to keep no overlap between my talk earlier at FPI and this one, so I removed that slide. But and it goes down to the physics of the problem. So a lot of structured proteins have what you call a time scale separation between slow modes and fast modes. They are not glassy. There are some dominant slow modes. So if you do something called TICA, you will get some eigenvalues which will be separated between fast and slow. RNAs are not like that. It's as close to glassy as it gets. So basically, now, is it 0 or 1? No, it's all binary. So if the system is very much on the glassy end of the spectrum, we use these replica exchange type methods. If it is well structured and everything, we use the AF to RAVE type methods.
Hi, thank you for the talk. So actually, I'm really curious about your opinions of you have this RAVE model which learns reaction coordinates for different molecules. So is it possible to train a universal model that automatically extracts coordinates from all the molecules? And do you think we need much more improvement in this aspect?
No, I think we are getting there. Even the code, So look, I'm running a group with chemistry and physics and biology students who are picking up their coding and everything. So things take time in a university setting, especially at a state school. But we are getting there. And if you check out the AF2 Race package, Da, who is my postdoc here, by the way, he's looking for industry positions if any of you are interested. He has done a very good job of automating these feature selection stuff so they can start applying to other domains also. It's getting there, and I'm happy to, if you send me an email, we can chat more.
I have a question. I have a question before we end. Can you tell us a little bit about the feature selection and how that occurs and what it's looking for? And does it pick up on anything interesting? And are those, when you compare them to experimental data?
Yeah, so for proteins, our initial bucket of features is all possible heavy atom distances and a bunch of dihedrals. That's a lot of features, right? So we start from them and we start reducing it. For the kinases, for example, we could go back and see that, the DFG thing, the dihedral is getting picked up as the most dominant feature. But it's still not as easy as you might think. Even, let's say if you have a linear model where 6 different terms have non-zero coefficients, which one is important, which one is not important? It's hard. So to explain which features matter, that's yet another hard problem. But we can do that in principle.
Have you compared to any experimental data besides adenylate kinase where we actually have the known population?
Mostly on kinases. On kinases and the S100 stuff, because I have an NMR collaborator, we are doing that.
That's awesome. Eric, let's give Pratyush a round of applause.